All right, hi, welcome to the last video of this unit. This is Gauss's law, so this will be the last thing we talk about here in Unit 8. And the way it kind of does is it just wraps everything up. It wraps it up onto all one single formula, okay? So Gauss's law relates the electric flux that we just talked about in the last video as it passes through a Gaussian surface that encloses charge. So they're going to take it a little bit further than what we talked about in the last video in the example problem. Where it's going to also focus on that charge. So the equation is going to be magnetic flux equals Q enclosed over epsilon naught. Now, what happens is this is also to kind of make it the full law, right? We would set it equal to that integral that we were talking about as well, right? Because we know flux also equals E dot dA. Now, this little circle added, that is the surface integral symbol. But again, don't let that freak you out because, you know, this is almost like a Calc 3 topic. But don't let that kind of scare you. Just remember, this answer is usually just equal to EA. Okay? So what is a Gaussian surface? So a Gaussian surface is a three-dimensional closed surface. The total electric flux is independent of the size of the Gaussian surface. The amount of enclosed charge, it remains constant. And these surfaces are constructed such that the electric field will enclose a charge that's either going to be perpendicular or parallel to different regions of the surface. And there in the bottom right, you can see some examples of surfaces. So this is where like KQ over R squared comes from. If you enclose a point charge in a sphere, when you do the infinitely long wire, right, you're going to do a cylinder. But the good thing is, like, if there's no charge passing through that surface, then it's just, you're going to have zero. Okay, zero part of the flux. Now, sometimes though they'll give you a function and talk about charge density. And this is where you'll get a lot of the your DQs, your this is where all the DQs will come from for the integral. And so there, and you can see there's three things. There's length, area, volume, right? So you can have a one-dimensional component, a two-dimensional piece, or a three-dimensional piece. So lambda is the linear charge density. What that means is charge per unit length. But if you have to find anything with an integral, I keep wanting to write capital Q, but we should write it lowercase. So you end up with dq dl, okay? And then you have the surface area, and basically all you're switching out is the A for an L. And then, so this is sigma, this is lambda, right? And so that'd be dq dA, and then the volume is rho, and that's going to be charge per volume. And so you would end up with not sigma, that's two-dimensional. You end up with rho equals dq dv, right? And so, I mean, that's where you get your integrals from, okay? And as long as this stuff is constant, like I said, you can pull it out and so forth. Now, what happens is there, when it comes to electricity and magnetism, there's a set of equations that fully describe electromagnetism, and it's Maxwell's equations. And these were compiled by James Clerk Maxwell, who did a lot in physics. He was one of the first to find the rings of Saturn. He took the first ever color photo. And then these equations that he puts together also describes light, because light is an electromagnetic wave. And so he described these equations, all kind of their interactions give us what we now know as light, or a further understanding of what light is. And the first of this set of equations is Gauss's law. Okay, so this Q enclosed over epsilon naught equals the surface integral of E dot dA. Okay, that is the first of the Maxwell's equations. All right, so let's look at an example problem of Gauss's law. So this one's going to be a little bit involved because this is directly from some AP materials or sources, and so we're going to look at one part of it. Now there's multiple parts to this question, but we're going to look at one single part. And so we have a spherical cloud of charge of radius r contains a total charge plus q with a non-uniform volume charge density that varies according to the equation. So if you see that non-volume charge density, that means you'd have to do heavy calculus. Okay, so it's saying from when it's inside, it's given by this rho r equals rho 0, 1 minus r, like little r over big R. And then when it's outside, the charge density is 0. Okay, so r is the distance from the center of the cloud. Express all algebraic answers in terms of q, r, and fundamental constants, and then determine the E. So what we're doing is determine the magnitude of E for r greater than r, right? So little r greater than big R. So basically what we're doing, and this is kind of like how easy this equation or this question is. So what we're doing is we're going to surround our surface, right, or our spherical cloud with a sphere on the outside. So basically what we do is we treat this as a point charge. So we would say Q enclosed over epsilon naught equals the integral of E dot dA. Okay. So again, typically the answer is just E times A. But again, we're doing a sphere. So our surface area that would pass through is 4 pi r squared. Okay. And then, here's how easy this one is. So it's E times 4 pi r squared equals Q enclosed over epsilon naught. Now the Q enclosed is big Q. Okay. And now we just simply solve this for E, and you end up with 1 over 4 pi epsilon naught times Q over, it's little r. Okay. And I wrote a big R. I just made it a point to say this was little r. But remember, this is K. So what basically we did is for this part, we just simply treat it as a point charge. Okay. Now, there are more parts to this question, okay, that, we will eventually go over, in particular, like write an expression for Q, right? So what is the amount of charge that is inside that spherical cloud? And then you can also do, the E field, right, inside the cloud. Okay. But wanted you guys just to get used to this, Gauss's law equation, how it works. Okay. And really see where the equation for a point charge comes from. All right. So that wraps up unit 8, right, for AP Physics C here in electricity and magnetism. And so we'll move into unit 9 where we'll talk about electric potential.